Thank you. Uh, Thank you for the introduction. As he mentioned, my name is Peter O'Reilly, and I'm very happy to be here and present the topic, how to spot bad data. It's a topic that I think will be of great interest. It's something that you can use in your daily work, and I think it's a novel approach to auditing your data. And while I mentioned that the title is How to Spot Bad Data, perhaps that's really too soft of a title. This technique potentially could spot fake or even fraudulent data. And there's a lot of useful applications for it. One, it could identify errors in your data, certain manipulative biases, costly processing inefficiencies, as well as other data irregularities. And in order to demonstrate this technique to you, I have to first give you a little bit background. That is the theory behind this. It entails some high-level mathematics. And with that, I think you'll have a greater appreciation of what we're trying to accomplish here. Something that requires an application of mathematical theory, but it also combines that with some very practical knowledge. And that knowledge is the owners of the data, that being you. So with that, one of the benefits of this auditing technique is that we're going to manipulate the data digitally. Unlike traditional auditing techniques that require a lot of trolling through papers, like big stacks of bank statements and whatnot, going through drawers full of paper, the nice thing about this approach is that we can all do it digitally. And what we're going to use as our tool is Microsoft Excel. Now, this approach isn't limited to just Microsoft Excel. The reason I chose Microsoft Excel is one, for its ubiquity, and two, I think pretty much everyone in this conference room is familiar with Microsoft Excel application. You could certainly use Lotus 123 or Quattro Pro or even OpenOffice, or even query the data directly from the database, which I'll touch upon later in this presentation. But for all intents and purposes, we're going to use Microsoft Excel. I'm just going to simulate working through a problem in Microsoft Excel. And, but first, I have to give you a little bit more background on this technique. It came about with this gentleman up on the screen, Simon Newcomb. He was an astronomer and a mathematician in the 19th century. And during his work, he kept referring to logarithm tables. This is, of course, pre-digital age, where you didn't have the benefits of a high-powered computer. You would actually refer to a book of tables to look up, in this case, logarithms. Speaking as a former actuary, when I was an actuarial student, I had to do a lot of that as well, not only with logarithms, but mortality tables, interest amortization. I'm sure many of you are familiar with tables of values as well. But what Mr. Newcomb had noticed over time was that in his book of logarithms, as an astronomer, he tended to wear out the beginning pages of the book more so than the rear end pages of the book. And so he theorized that, this is kind of peculiar. Maybe there's something to this, more to this. And he had this hypothesis that maybe there's a case for natural numbers, or a natural order of numbers, if you will. So he did much research into that hypothesis, and he actually published a paper in an academic journal. This is back in 1881, quite some time ago. And that research really, while well received, it didn't go anywhere, so to speak. Then he stumbled upon this gentleman, Frank Benford. He was a physicist working at General Electric Research Laboratories in Schenectady, New York, back in the 1920s. And oddly enough, he discovered the same issue with him wearing out the beginning pages of his book, his logarithmic book, as a physicist. So he expanded upon the research of Simon Newcomb, and he went so far as to handwrite out thousands of lists of numbers. In fact, he took a Reader's Digest magazine, and at that time it was a pretty thick periodical, and he flipped through and recorded over 6,000 numbers and used that as part of his research. And he came up with this law known as Benford's law that he published in a paper in 1938. It was actually in an academic journal called the Proceedings of the American Philosophical Society. And basically the feedback that he got at the time was, it's just a mere curious observation. So really the work of Newcomb and Benford really slept dormant for many decades, if not close to 100 years. And it wasn't until the age of digital computing in the 1990s that this technique really, this mathematical law and its technique, its application of that mathematical law really came into being. And in fact, it got worldwide prominence back in 2009, the Iranian presidential election, where folks had detected fraud with that election, with people fudging the election results. And the approach that they used was the technique that I'm going to demonstrate to you in a moment. I can say from personal experience that I've actually audited 3 municipal elections for a very large municipality, and I'm very happy to report that I didn't identify any potential fraud with that election. But I do know it is a very effective measure, and with the availability of information that's available digitally, thanks to the county clerk's office, it makes it very possible to proceed with this technique. Even more recently, in 2016, this technique was touched upon in the Hollywood movie titled The Accountants, that starred Ben Affleck. I don't know if anyone's seen that movie, but yeah, it was an action thriller, and he was basically an accounting genius, and he actually used this technique in the movie. So not only does it apply to election data, but you can also use it for financial data, and that's why we're all here, is to hear me talk about auditing financial data, which I'll do in a moment. So here's a formula. This is the proof of the pudding. This is the genesis of Frank Benford's work. This is the function. It's known as a probability distribution function, or more accurately, a logarithmic probability distribution function. As you can see in this mathematical function, it uses log, to no surprise, because he kept referring back to his logarithmic table. But after all of his research and whatnot, this is the formula that he came up with that comprises the Benford law. Now, I'm not going to dispel with you the heavy-duty math behind this technique, thankfully and mercifully. Instead, I'm going to look at the output of this function on this next slide. And this next slide is the output of that function, that probability distribution function. So for those of you who are familiar with probability theory, right, you have to add up all possible outcomes, and that should sum up to 1, or meaning 100%, meaning that you can for all possible outcomes. And that's what is represented in this table here. So just a little bit more background. So I have digits 1 through 9. And with each respective digit, I have a probability assigned to that value, and that's using Benford's formula. So as you can see, the digit number 1 has a probability of roughly 30.1% chance of occurring. And what I mean by that is in the natural world with data, the number 1 should appear most frequently, and then the number 2 should appear next as most frequent, and the number 2 should appear more frequently than the number 3, and the number 3 should appear more frequently than the number 4, so on and so forth, whereby the number 9 is the least popular number in the natural world, if you will. And that's the basis of Simon Newcomb and Frank Benford's work. And it's represented in this table here. I'll be referring back to this table in a moment as I demonstrate an actual calculation with you. So the name of this technique or this law, this mathematical law, is called the first significant digit law. It's also known as Benford's law or Newcomb-Benford's law, if you will. And with that, I have to now define to you what it means to be a significant digit. And as you can see from the screen here behind me, it's just a few simple rules. And I think it's pretty intuitive as we step through. So what is a significant digit? By definition, it is all non-zero digits are significant. Your simple counting numbers, 1 through 9. 0 digits between non-zero digits are significant, as represented by the examples seen below. Leading zeros are never significant. And numbers with a decimal point that contain trailing zeros are significant. However, pardon me, the significance is only applicable to the amount of precision in your data. So for example, since we're talking about financial data, that's dollars and cents, it's only significant down to the second digit after the decimal point. That's a small detail to keep mind of, but you'll see in a moment when we run through an example. So this next slide provides some examples of what are significant digits. I have a list of numbers there, and within each number, the digits represented in the red font are significant digits. And while you take a minute to absorb that, I'm just gonna get a sip of water. All right, so now that I've explained what is a significant digit, now I must tell you what type of data best works with this type of auditing approach. And so with that, you want to have data that's drawn from a random sample, a large sample size as well. The larger, the better. No bounded maximum value, as well as sufficient variability, and counting or measured based numbers. Now, within these requirements, I think you can think of some financial data that you may have that is suitable for this type of application, and I will provide you one in a moment. Conversely, what this technique does not work well with, the types of data are sequentially assigned numbers, such as your purchase orders, your check numbers, invoice numbers, numbers that are influenced by human thoughts, like a psychological component, like it's $9.99, accounts with a large firm-specific numbers, such as $10 for refunds or dog licenses or marriage licenses, where it's always the same amount for each transaction, as well as accounts with a minimum or a maximum that are bounded by a minimum or a maximum. Now that I've explained what a significant digit is and what this data is best for and provided you with the theory, now let's go into and actually run through an example. An example that I'm presenting to you today is a listing of daily tax receipt data. It's actually for a very large municipality. And not to keep anyone in suspense, this data actually checks out, so you need not worry if you're from that municipality, that beloved municipality. So I have 2 columns here from spreadsheet screenshot from Microsoft Excel. First column is date, and the second column is daily tax receipts. For argument's sake, you can ignore column A. I just put that up there for comfort level. But what we're really going to focus on is column B, that being our daily tax receipts. And if you can imagine, without having the benefit of Excel in front of me, it goes on and on and on for thousands of records. So our first task is to extract the first significant digit from each daily tax receipt. And how we're going to accomplish that task is to use Microsoft Excel. And even more specifically, we're going to use the left function that's built into Microsoft Excel. And this left function takes two parameters, or two arguments, if you will. The first being the text. That is the text that you want to parse out, the first significant digit. And then the second argument is the number of characters, meaning how many characters starting from the left do you want to parse out from that text. In our case, it's only one, the first significant digit. And the next slide will make things even more concrete for us. So what I have here, building upon the prior slide where I showed our original data set of dates and tax receipts, daily tax receipts, I'm applying the left function in column C to parse out the first significant digit for each daily tax receipt. Now, since I don't have the benefit of Microsoft Excel to show you the contents within each respective cell contained in column C, I placed that text in column D. So what I mean by that is, for argument's sake, in cell C2, I would type in equals left, open paren, B2, comma 1, close paren, and hit enter, and that would return a number 5 in C2, which would give me the 5 as the first significant digit for the tax receipt on September 25th. So I'm going to do that left function all the way down my entire column of tax receipts. And then the next step, once we've parsed out the significant digit, is to simply count or enumerate how many of each digit is in that data. How many significant digits are in the data set for each respective digit, 1 through 9. You'll see that in a moment, but we're going to use the Microsoft Excel function, countif. And the countif function accepts two arguments. The first being the range. That's going to be our entire range of tax receipt data, just the dollar amounts in the single column. And then the second argument is going to be our criteria, which is simply the number 1 or the number 2 or the number 3, so on and so forth, down to number 9. And as you will see on the next slide, I have an example of that. So in column F, we have our digits 1 through 9. That's self-explanatory. In column G, that is the count, that being how many tax receipts have a first significant digit containing the number 1. That count is 1402, and how I accomplished that was by using the countif function in that column, in column G, by typing in countif and then the cell range of all of my tax receipt data, and then specifying the number 1 as the criteria. So with the countif function, your range, you could use a name range if you're more comfortable with that in Excel, or you can easily use the alphanumeric syntax as well. So as you can see, I did it for each digit, 1 through 9, and you have a total count of 4,768. That's a pretty large and extensive data set that we're working with. Pardon me. And now we're back to the table that I introduced to you originally. This is the Benford's probability table, if you will. So what I want you to take note with this table is this is what we're expecting, the expected frequency for each digit in our data set. So what I mean by that is, for example, the number 9, within our daily tax receipts, I'm expecting a first significant digit of 9 to occur roughly 4.6% of the time within the data. So now I'm going to marry my calculated results, that being what I actually experience in my data set, that being the tax receipts, and I'm going to compare that with the expected frequency, or the Benford probability table, if you will. And I simply have the comparison there. As you can see, with my significant digits, how I calculated the actual frequency, that's taking the raw count and dividing it by the total count of all digits. So that would, for digit number 1, that would be 1402 divided by 4768, and that would give me an actual frequency of 29.40%. And I would proceed to do the same for all the remaining digits. And as you would expect, the total should total up to be 100%. And likewise, for my probability table, accounting for all possible outcomes, that should be 100% as well. So I've got my actual, I've got my expected, and looking at the 2 columns of percentages, they look pretty close, which is a good thing. So why not take this one more step further since we're in Microsoft Excel, and why don't we proceed with plotting out the results so that we can get a better idea visually. And on the next slide, I did just that. And as you can see, this is a bar chart that was done in Microsoft Excel. And I'm comparing the actual versus expected frequency for each significant digit, 1 through 9. And the thing to take note of with this, and the reason why there's a thumbs up, is that the respective pairings of the bar charts are pretty close in height to each other. So what that means is my actual experience is matching or closely tracking what I would expect based upon Benford's law. So this is a good result. Now I want to show you what a bad result is, and one that I intently faked the data. And how I faked the data was, I took my original spreadsheet containing the tax receipts, and I substituted in each cell value for the tax receipt. I replaced it, the actual dollar amount, and I put in the Microsoft Excel RAND function, which is a random number generator. Now you might think, oh, random number generator, that sounds pretty kosher. However, this random number generator assumes a uniform distribution of results. So what that means in plainer terms is that drawing a 1 from this function is equally likely as drawing a 2, and drawing a 2 is equally likely as drawing a number 3. So it's basically a 1 in 9 chance of drawing any particular number, which obviously is counter to the natural law of numbers, where the number 1 should appear more frequently than the number 2, the number 2 more frequently than the number 3, so on and so forth. So this is an example of me faking the data and going through the steps of using the left function in Excel and the countif function in Excel as well, and comparing the frequencies numerically and then plotting it. And as you can see from this bar chart, that there is a lot of discrepancy between the heights of the actual versus expected for each individual significant digit. Next, I present you another way. As I mentioned before, you don't necessarily need to use a spreadsheet program to perform this task. If you're even more technically inclined, if there's any IT people in here or someone that's comfortable with writing a database query, you can even do this in a more express manner. It's probably I'm assuming there's not many people that know this, but I just put it here for the sake of completeness. As you will see in this syntax, which may be Greek to you, we do use the left function and the count function as well to query the database directly. But I only mention this since, in all likelihood, since you are working with data that most likely originates from a database, you may be able to even cut out another step or have someone help you cut out one or more steps in doing your analysis. So just to recap on this method, the application of Benford's law, it really boils down to 3 simple steps that using the Excel function left, as well as the Excel function countif to enumerate all the significant digits within our data set. And then to visually analyze and interpret the results, we're going to plot it as a bar chart. And with that, there's a whole lot more that can be explored with this technique. There's even a second significant digit test, as well as a third and a fourth and a fifth. However, for all practical purposes, it really is overkill, especially for finance officers. I would say the first significant digit test is more than sufficient. Additionally, if you want to apply some even more mathematical rigor to determining the outcome, whether our data looks potentially fake or not, we could take the results of the actual versus expected and perform a statistical test on it, hypothesis test, known as chi-square. However, once again, that's really beyond the scope and reach of many finance officers. I only mention that as a matter of completeness. And lastly, this technique, while it is really, really good at detecting potentially bad data, it is by no means absolute proof. It's not like a DNA test. However, it is a pretty sound method to performing such audits on your data to identify any potential errors or possibility of it being fraudulent. And with that, that's really everything that I have regarding this technique. And I hope you give it a look. And I think it's a really useful tool. Even, I should mention, as an auditing measure, it's pretty quick and dirty. And if you did spot some irregularities using this technique, well, you can always resort to more classical approaches to auditing data that are also much more time intensive as well. And I cover this technique in even greater detail in chapter 25 of a book that I've recently written covering local public finance. And with that, I just would like to thank the audience for giving me the opportunity to speak to you all today.